This is video 5 of the categorical analysis, and we'll learn about chi-square independent test. Chi-square independent test is another test using chi-square distribution. This time we have two variables where both are categorical variables. Using chi-square independent test, we can test if there is an association between two variables. For example, a new drug is being compared to an existing drug for its effectiveness in relieving headache pain. 100 subjects who suffer from chronic headaches are randomly assigned to either group 1, existing drug, group 2, new drug, group 3, sugar pill. Subject record whether or not they experience relief from headache pain within 60 minutes. Here we see there are two categorical variables. The first variable, categorical variable, is a drug kind, and the second variable is if the subject has a headache or not. There are three categories in the first variable, drug kind, and two categories in headache variable. In practice, two variables can have various different numbers of categories, not only 3, 2, but they can have 5, 4, and 10, 10, whatever. Chi-square independent test process looks very similar to the one the chi-square goodness of it test. Step 2, 3, 4 should look very familiar, and it actually looks almost identical. The difference are how to calculate EI and the degrees of freedom. So here is a little note how to calculate those. The null hypothesis is the two variables are not associated, and the alternative hypothesis is the two variables are associated. The test statistics is again measuring how far the observed frequency is from the expected frequency if the two variables are not associated. The expected value can be calculated as the row total times column total divided by the total numbers for each categories. And we'll show that in the example. And once calculated, the test statistics can be compared to the critical chi-square table value right there with the degrees of freedom of the number of rows minus 1 times the number of rows, the number of columns minus 1. P-value can be calculated based on that, the test statistics as well. We recall the previous example we looked at for two-sample proportion test. This is the simplest two categorical variable case having 2 by 2 contingency table. Each 4 numbers in the middle is observed values, and expected values can be calculated assuming there is no association between two variables. The expected value for each cell is in the parentheses. For example, 400 times 836 divided by 1000 is 334.4, and 600 times 164 divided by 1000 is 98.4, and the other ones are calculated in a similar way. Then the test statistics is again the sum of squared difference. Again, we know OI and EI. So the sum of the square difference between observed and expected value divided by expected value for each categories, and you just sum up, and that will be your test statistics. And again, we're not going to probably do that by hand. The data is in the format that we can easily use and available in text form, TXT form in the module 6. And you want to save it in your own directory. Then you can call the data using read.txt DELIM function, then the CHISQ.test function will execute the chi-square independent test. Here, the test statistics is 2.9786. The degrees of freedom is the number of rows, which is 2 minus 1. 2 minus 1 is 1, times the number of column, 2 minus 1, which is 1. So 1 times 1 is 1. There is no statistically significant difference in passing rate, their performance, between online and in-person basic statistics course, since p-value is 0.08437, which is not less than the significance level, 0.05. So those two numbers that we talked about was not statistically significantly different, even though one number is slightly higher than the other number. When one or more of the expected cell frequency is less than 5, chi-square test is not quite reliable, and the Fisher's exact test is the better test. For this particular example, all expected frequencies are larger than 5, as you can see right here. Every number is actually larger than 5. Thus, chi-square test would work just fine. Here we are running the Fisher's exact test for a demonstration purpose. Using Fisher.test function, we have the p-value of 0.0843. No, this one. 0.08108. Thus, we make the same conclusion as before. Notice that the p-value from Fisher's exact test is similar to the p-value from chi-square test. If one or more of the expected cell frequency is less than 5, the p-value might be vastly different. Note that at the bottom of the output, there's an odds ratio, which is 0.7330 here. This is a common measure to analyze categorical data, especially 2x2 situation. We'll talk about what odds ratio is and how to interpret it in the next video.